And now, okay, now I can see everything. Okay, well, thanks again for having me here. I'm always glad to talk to this group. You're one of the most engaging and interesting groups that I have regular interactions with, so it's always good to be here. Today we're going to be talking about the James Webb Space Telescope. Now, I'm assuming you're all at least moderately curious about that, and I hope to at least take whatever level you're coming in at and raise that. There's a lot more to it than gets covered in a lot of the mainstream coverage. And that's just because it's a very complicated machine, and it's also doing some very complicated science. And I think it's all very fascinating, and it's not actually that complicated when you really break it down. The conceptual aspects are within grasp of anyone that has just a little bit of interest, I think. And the things that make it a little bit out of reach for mainstream coverage is that it's hard to break down these points into 30-second sound bites in the news. So what I want to do today is give you an overview of what its mission really is about, and then some of the engineering work behind it on the technical side. I'm going to try and break it down, though, so it's not too complicated. I don't want to get super technical. If you have questions, though, I'm happy to do that. And for the sake of the recording, maybe we can have intervals where we ask questions. So I'll try to remind myself to break every now and then and do an open Q&A so we don't go too far from the topic you might have had a question about. But we can also save questions for the end here. Now, let me just try one more time. I seem to have lost my window yet again. I hope it's coming through for you. Let me just try and pull it back for myself. Is that looking good? John, can you just nod if you're seeing my slides? Okay, good deal. All right, well, let's just dive into it. There's a lot to cover, probably more than we can even get through, so we'll just see where things go. And feel free to throw questions in the chat, too, and I can try and take those as they come for those of you who are in front of a computer at the moment. Okay, so what is the Webb? Well, a lot of times the Webb is described as the successor to the Hubble Space Telescope, and in a way that's true. In a broad sense, it is a orbiting observatory. It's a space telescope, just generally speaking, and it does come after Hubble, and it was conceived of and put into play right after the Hubble was launched. The plans for a successor of sorts were actually in the works well before Hubble launched. But the mission that it's designed to fulfill is actually a little bit different. When it comes to big budget government agencies like the European Space Agency, NASA, they don't necessarily repeat their own work. So it's not like it's just the same thing as the Hubble Space Telescope, just bigger. It actually has a slightly different mission goal. But again, this is a little bit hard to convey in short headlines, so I want to add a little bit more subtlety to that. But before we go on, just take a look at this picture, and hopefully for those of you in the library, you can see these images up close, and if the details are a little bit small, I'll try to highlight the important parts. But notice the NASA logo reflecting in the hexagonal mirror segments here. It's a very minor thing, but in a lot of the CG renderings that NASA publicizes, for whatever reason, they often show the mirror surface as heavily dimpled, and I think they're just trying to show that it's reflective and that it's the mirror surface, but it often looks very out of shape or a little bit deformed. But in reality, the mirror is one of the most precisely ground optical surfaces ever constructed, especially on this scale. And this isn't unusual for an orbiting observatory or for any large professional ground-based observatory for that matter. They often will divide them into segments just for the practicality of manufacturing and deployment. It has nothing to do with the optics. When they're all put together, they basically behave as one large, singular curved surface. The hexagonal segments are there as a necessity in order to move something that large and handle the mechanical engineering sides of things. But it's not for any optical reason. In fact, it introduces, some minor problems that they can correct for in the software. But notice how crisp and sharp that image is. So when you see, later on, we'll actually see a few images that show this, where the mirror is seen rotating and then the images reflected in it are highly distorted. That's just not realistic. It's a very minor thing. It's more of an artistic thing, but now you know the difference. Okay, so The Webb telescope, it serves a slightly different mission goal than the Hubble Space Telescope. The Hubble Space Telescope focused mostly on the visible wavelengths of light and then a little bit of the near infrared and a little bit of the ultraviolet as well. Now, it's in low Earth orbit, so it was able to be serviceable. We could change instruments out. There was that famous kerfuffle with the mirrors not being aligned originally. They were machined to different designs. They were machined correctly, but the instructions were not checked beforehand, and it's a big mess and worth another discussion another day. But because it was in low Earth orbit, only a couple hundred miles away from the Earth or above the Earth's surface, it was serviceable by the astronauts. And you've probably seen those famous images of Story Musgrave doing an EVA outside the shuttle, servicing different elements and components on the Hubble. That is not possible with the James Webb. It is far away from the Earth for reasons that will become more clear as we go on. The James Webb primarily is focusing on the infrared wavelengths. So the pictures that you've seen so far of Hubble, they often show these rich, full-color images of objects that, if any of you are amateur astronomers, you've probably seen many of them through your own telescopes. The famous Pillars of Creation, the Eagle Nebula, that's an object that you can see on any summer night, even with a pretty modest telescope. Obviously, it won't have the same detail or color richness to it, but it's an object that you can see more or less in the same form that the Hubble will image it in. Now, it's false color because they're assigning some of the wavelengths that are outside of the eye's range of detection. They're assigning those values that are inside of that optical window so that our eyes can see them. So in other words, some of the infrared light is assigned a visible wavelength value, and then they compress all the colors in order to make room for all of the visible wavelengths plus the ones that our eyes can't see, all in the same image. So that's how when you get a print image or an image on your computer, you're seeing more colors than the eye would see, even if it did have that sensitivity. Now, the Webb telescope is going to be moving in the mid to near infrared almost exclusively. In fact, it doesn't see in the visible light. That's not where they're looking at all with this telescope. Now, the Webb does two things really well. It sees in the infrared, so that's an instrumentation choice. The detectors are all tuned to be very sensitive to infrared wavelengths. And then the second thing is that the mirror itself is tuned to infrared wavelengths, and its position in space is way out away from the Earth to avoid that radiation. And that radiation contributes to the infrared, and I'll show you much more about that in just a few moments. The gold color that you see on that is specifically because it's going to be looking in the infrared, and gold is much more reflective to infrared, whereas a typical mirror that you would see on even a large observatory scope on the Earth, they tend to reflect visible light very well because they're also incorporating those wavelengths and studying them. But in the Webb's case, it's almost exclusively in the mid to near infrared, so it doesn't have any need to be tuned for visible light. So the instruments are designed for infrared, as is the mirror. So it would actually be completely different than Hubble in that regard. The images that we'll see that will come back from it in probably June or July of this year, depending on how things go, they are going to look a little different than we're used to seeing, because Hubble, there are a lot of colors that we're still familiar with. If you've looked at pictures of, again, the Eagle Nebula, the Orion Nebula, amateur astrophotographers are able to get pictures that somewhat resemble that with their own equipment in their backyards. And the color palette is somewhat similar. There's a little bit of artistic stretching that goes on, but the root of it is the same as what your eye would see. And so you're seeing images that more or less correspond to the ranges that the human eye would see. And when we go into the infrared, the near and the mid-infrared, our eyes are not able to detect those wavelengths whatsoever. So all of the images that we see from the Webb are going to be, by necessity, false color, meaning those infrared wavelengths are assigned wavelengths in the visible range, and then they're going to have to choose how to do that. And we'll look more at that in a little bit. But that's the biggest difference, is that the Webb is going to be seeing infrared exclusively, whereas Hubble was primarily visible with a little bit of ultraviolet. Now, there's not a lot of overlap between the two. Hubble was focusing on all sorts of objects, and it was in some ways the most significant orbiting observatory, and is still contributing to this day. It's an incredible work of engineering and art, I would almost say. But it's still going, and it's working on the same things, visible and a little bit of the near infrared. The Webb telescope is not just doing the same thing but more. It's actually looking in different areas altogether, both in terms of its access to the sky, the coverage that it will see. It can't pivot around and move nearly as much as the Hubble could. But it's also studying things that the Hubble has not seen. So it's Hubble, in a way, has identified areas that are very interesting to look at, but we don't know what's in there yet. And now that the Webb is going to be pursuing those areas of the infrared, we know where to look. We don't know exactly what we're going to see there, though we have a pretty good idea. So let's take a look at a diagram of the scope itself. It's kind of a weird looking thing. It does not resemble like the Hubble. It sort of looks like what you'd expect of a telescope. It's got the big mirror and the tube, then the solar panels. This looks very strange. Well, there's two big sides to it. There's the Earth-facing side, or more accurately, the Sun-facing side, and that's the bottom here. So the spacecraft bus, that's this big box down here, and then the sun shades, these are permanently going to be oriented towards the sun. And then there's a solar panel that will pick up some of the sun's energy to convert it to usable electricity for the systems on board. Then there's the optical side, which is permanently facing away from the sun and the Earth, and that's where the mirrors are. Now, this entire assembly here, the gold mirrors and then those three truss tubes and the secondary mirror, those are collectively referred to as the optical telescope element, the OTE. You might see that referenced in some documents or images at some point, but this is the side where the imaging takes place. Then on the back side of that, there's the integrated science instrument module, and that's where all the detectors and the cooling equipment are housed. So that is a little, we'll talk about that a little bit later, but basically the challenge there from the engineering standpoint is that you don't want any heat on the optical side of the telescope, but then you have this big box of electronics that, as you know, generates a little bit of electricity and therefore waste heat. And so that was a very interesting problem. And we'll explore why that is. But let's first of all look at how it got into orbit. We are now towards the end of this timeline here, where we've passed the launch on Christmas Day. Then the sun shield was the very first thing that was deployed. Now, the sunshade by itself, or the sun shield, is an incredible piece of engineering. Everything else on the telescope, and pretty much everything that's ever been put into orbit, more or less, is what engineers call deterministic. So like a hinge, when it opens, it has a stored state and an open state. There's no other option, barring any sort of malfunction where it gets stuck in the middle, something like that. But it doesn't have any in-between. It doesn't crumple up, it doesn't crinkle, it doesn't fall off to the side. You know exactly where it's going to be when it's actuated and fully deployed. Now, the sun shield posed a huge problem because it's like packing a parachute or folding up a blanket. You don't know exactly where every little piece of it's going to be. This is a non-deterministic packing arrangement, and you can think of it, the simplest case is like putting a piece of yarn on a table and then pushing on one end. You know that the end points, if you're grabbing the ends, it's going to go in this way, but as to which way it folds in the middle, is it going to bend halfway or curl around or have maybe 3 or 4 little loops, hard to predict exactly what's going to happen there. So with the sun shield, there were a huge amount of issues with that, and this is one of the reasons it's been delayed so many years. Originally it was scheduled to launch, I think at one point as early as 2013, but obviously it's been pushed back many times. One of the issues with the sun shield, though, is just this, is that it's a non-deterministic packing. And the problem with that is that when you stow it and you can't predict exactly where every single piece is going to go, that means when you're doing the reverse, when you're deploying it, if any part of that didn't get packed within the limits of its space, or if it folds on itself twice and then causes a tear or something like that, then you have a critical issue, because the sun shield prevents the sun's energy from reaching the optical side, which is where all the imaging is going to happen. And it is incredibly important that this telescope remain cold. So I have a video later on to show you of the actual sun shield deployment and some of the issues that went into that. But that took a lot of novel engineering. And in fact, they were using some sort of origami folding techniques in order to improve the packing accuracy and therefore the deployment reliability. Now, the sun shield goes out first because the telescope has to cool down. As to why it cools down, we'll go into that in a lot more detail shortly. But that was the reason. The very first thing is that it has to start cooling down to give itself time to bleed off that extra thermal energy that it has from being stowed and launched from the Earth's surface. Now, in space, there's only one mode of heat transport. Heat transport is just the way thermal energy moves from one surface or medium to another. Here on Earth's surface, on a daily basis, we're used to encountering all three types. You have conduction, that's when an object is touching another object, like when you pick up a cold glass of water, you feel that heat transfer from hot to cold. Then you have convection, which is like the wind blowing, and that's the wind chill effect, which we're all too familiar with. And then you have radiation transfer, and radiation is like feeling the sun's warmth come through a window. And in space, you lose those first two modes of conduction and convection because you're not in contact with anything. So the James Webb has all this thermal energy from being stored on Earth's surface at more or less room temperature. And then there's a little bit of an upswell in temperature as it launches. There's just a lot of heat generated in that process, obviously. And once it reaches the vacuum of space, it no longer has anything to touch. So all that conduction mode is lost. All that energy is got to be radiated outward. There's also no wind blowing in space because it's a vacuum. There are a few particles, a few parts per million, deeper in space, a few parts per billion, but that's not nearly enough to have a noticeable or useful effect in practice. It's more of over maybe 100 years it would start to accumulate some of that heat loss. So basically, all of the heat has to be lost by radiating away from the telescope. And that takes a very long time. It all has to be lost through a process or through a phenomenon known as Planck radiation, where any object that has thermal energy also radiates a certain wavelength of light. And that's actually partly why it needs to be so far away from Earth, but I'll tie this together later on. But just hold that thought in the back of your mind for now. But because it has to lose energy through, or cool down effectively, through radiative processes only, no convection, no conduction, they had to immediately deploy the sun shield in order to start that process on the way out to the Lagrange 2 point, the Earth-Sun Lagrange 2 point. We'll talk about what that is also as well. Then on the way out there, it's obviously deploying the mirrors and getting some things set up, and then right now we're actually aligning the different mirrors, all those 18 segments. They are individually aimed at the secondary mirror, so it basically is 18 separate telescopes right now, and then they have to basically do some fine-tuning and adjustments and make sure that they all function as one single coherent plane or optical surface. So that curve has to be consistent across all of them, not just 18 individual segments, which is not very helpful, obviously. And then one common question that comes up is how long will it be till we get images back? Well, the instrument calibration process, that's going to take a little bit of time. The estimates right now are roughly the summer solstice, so probably end of June. They're still commissioning the instruments, so there's a long boot up process. It's not like your computer where you turn it on and a minute later it's ready to go. There's a very complicated startup procedure for a lot of these instruments. They have to reach a critical temperature first because they're only designed to operate in very cold temperatures. Once they reach that, then they have to do all sorts of checks, and I'm not too familiar with all the individual procedures, but the overview is that you have to basically make sure that the instruments work step by step. So you do fault isolation from the beginning. So if there is an issue with an instrument, you don't just turn all of it on and then try and troubleshoot it that way. You do a staggered approach where you check one system, then add the next one on, and then if that checks out, then you add the next one, and so on. And then make sure that all the telecommunications are working, so we're able to talk to the scope, the instrument's coming back and feeding us data in the range that we expect to see it, all sorts of things. And there's a lot of minor fine-tuning that has to go on. And they also have to keep cooling down because it's not a quick process. It can take weeks to months depending on which instrument we're talking about. But once that's done and then the alignment is completed, we should start seeing our first science images around June or July of this year. That, of course, could change. It's subject to a lot of variables. But the good news is that we are past the difficult part right now. The launch is obviously the most critical and highest risk part of any mission. There's no guarantee that that will work. Engineers don't deal with certainties; they deal with probabilities. And you may have seen actually in the weeks and days leading up to the launch, there were some pretty high level NASA administrators getting out there and saying that we're 100% confident that it's going to go off without a hitch. And that I understand the necessity of building confidence with the public, but that's just simply not true. There, in some ways, I get, because they have such a small space and a small platform, why they want to say that, and the quickest way to sound confident is to just say you're confident. But it doesn't sound as good to say that there's a good likelihood. But I don't think it takes that much extra effort to go and explain all the different systems that they've had to check. Part of the initial delay with this telescope was that they identified, I think it was close to 400 single point failures on the telescope about 6 or 7 years ago. A single point failure is basically any one failure that doesn't have an embedded redundancy to correct itself. So if that one single point fails, the entire mission is compromised in some way, shape, or form. Some of them catastrophically. For example, the sun shield, if those 5 layers of aluminized foil did not deploy, there would be no mission. It doesn't matter, even though in some ways it's very similar to the emergency blankets that you can buy at Walmart for $1. It's a little bit more than that, but it's roughly that concept. So you'd think this would be in some ways the cheapest and easiest part to build. It's not. It's very complicated, and there's so much riding on it that the fragility of it to this importance and the criticality is very, very high. So it doesn't matter how inexpensive it is to manufacture relative to the other optical equipment on board, or the telemetry, instrumentation, all of that stuff that's very expensive traditionally. It will not work if it's hot, so it doesn't matter. And that's one of the reasons that they delayed it, is like they needed to figure out how to make the system more reliable, make sure that every system had some sort of redundancy, or minimize the risk. So if there is a single point failure, you don't want that failure to propagate through other systems or have cross dependencies where one system is depending on what just failed. You want to have alternate routes for information to get through. And this applies to everything. This isn't just one aspect. This can be mechanically, this can be with the guidance and navigation, this can be with the optical side. All of the instruments on board, both the detectors and then the spacecraft operations, so like the star trackers, the alignment equipment, all of that has to be able to work with with some failures, because nothing is ever perfect. But with all of that being done, the chances of failure go down dramatically, and I think that is something to be celebrated. And it's kind of disappointing when they get out and say, well, it's going to work perfectly 100%. Maybe it's just my preference, but I think it's more interesting when you know that it's not perfect, but we've by orders of magnitude increased the likelihood that it's going to work. That shows, I don't know, a little bit more depth to it, and I think that's important to understand. But there are no certainties in spaceflight, of all things. But the fact that we made it past the launch and then past the critical deployment of the sun shield means that now the things that could go wrong are much smaller. So there's almost, to my knowledge, there's no critical failure that could happen that would mean we would have no Webb mission from here on out. The things that could fail would be small or minor, or it might limit one instrument's capability, but the mission as a whole would go on. And it's not a single pronged mission, it's a multi-tiered mission. There's 4 major instruments on board, and they're all doing a lot of different things in tandem. So it's not there's no risk that we will not get information back at this point. So if you were worried about that, we are over the hard part. Now it's just a waiting game for the scientists to finish aligning, calibrating, and turning everything on, and then we should start seeing science-grade images come back June or July of this year, but certainly no earlier. I did hear that they were considering re-imaging the Hubble Deep Field, that famous image that they sometimes refer to as a galactic core sample that goes way back in time, showing some of the earliest galaxies, the elliptical galaxies that had just formed. And the Hubble Deep Field is again, a very fascinating story. Look that up if you haven't seen that. the Webb is going to image that area of the sky. I don't know if it'll be the very first image. It might be on the docket for at some point this year, is what I've heard. But stay tuned. If we don't have a chance to talk together about that, look that up, and I will almost certainly bring it up next time we're together, because it's just, I cannot wait to see that image. We're going to see a whole new level of depth to that in ways that have not been possible before. Okay, so let's take a look at the scope itself. I want to show you an excellent video here, and I'm going to put the link in the chat for those of you who want to watch the whole thing. It's a really long clip, but it does a fantastic job of explaining the overall design goals, and also gives animations of the scope itself. And because this thing is so weird looking and unusual, I think it's helpful to see it in motion. And I'll be sure to follow up Cheryl and send you the links, so if you want to pass these on for those who don't have access to their computers right now, then they can take a look.
In the beginning, our universe was very hot and dense. As the universe cooled down, the electrons interacted with the nuclei, forming the first atoms. A few 100 million years later, the first stars and eventually galaxies appeared. But how did they form? This thing will help us understand. A $10 billion time machine, which has been in development for over 20 years. Imagine that you are 65 million light years away from Earth, somewhere in the Virgo cluster, and you have a very powerful telescope which you can use to study the Earth. Taking a look through the telescope, you would be able to see what dinosaurs looked like on our planet. Of course, we will face many obstacles along the way, but we are talking about an incredibly powerful telescope, right? The James Webb Space Telescope is exactly that. It is 100 times more powerful than the Hubble telescope. Just look at the comparison of the sizes of their primary mirrors. And yet, James Webb's mirror is 113 kilograms, 249 pounds lighter. The telescope works in the infrared spectrum. The infrared radiation can penetrate the dust cloud and allow us to see the stars forming within. Additionally, Einstein's theory of relativity states that the space between objects in our universe expands, and so does light. As the light from the first stars and galaxies travels in our direction, its waves lengthen and the light becomes infrared, also known as redshift. Every time you look up at the night sky, just know that there are many stars and galaxies, the light of which stretched and became invisible or too faint for you to see. So here's a question. How is the James Webb Space Telescope supposed to detect that light? It will be assisted by a huge mirror, which will increase the amount of collected light. The more light, the more detailed the image. The mirror is made with 18 hexagonal segments, each one 1.32 meters, 4.3 feet in diameter. This shape will enable the crew to fold the mirror on Earth and unfold it in space. Then, the focus of the mirror will be calibrated by shifting the various segments with an accuracy of 1 to 10,000, 1/10,000th of the thickness of a human hair. The light is collected onto the secondary mirror. Then it is reflected and sent to the scientific tools. After it is filtered, it is then focused on the hypersensitive infrared detectors, at which point the photons are converted into electrical voltage. The actual telescope is equipped with 4 tools. NIRCam is the telescope's primary imager in the near-infrared range. 10 sensitive detectors allow it to detect the light of the first stars and galaxies. In addition, NIRCam is equipped with chronographs. And what are they? Imagine that you're blocking the sun with your hand. By blocking the bright light, you can see the road ahead of you. A chronograph follows a similar principle. This function will allow researchers to see more faintly lit stars, galaxies, and even take photos of exoplanets. But NIRCam cannot show us everything we need to know about the physical properties of a planet. Is there water? Air? Impossible to say. Therefore, another tool called NIRSpec will be working with the same range. By studying the spectrum of light emitted by an object, we can tell its mass, temperature, and chemical composition. The atoms and molecules of an object leave their mark on the spectrum in the form of black lines. But to analyze the faintest light, the telescope has to stare at the object for over 100 hours, which is ages. But surely the scientists did not spend 10 years working in vain. To avoid wasting the telescope resources on a single object, the NIRS is equipped with a superpower to provide spectroscopies of hundreds of objects at once, which was achieved by developing a new technology called micro-shutter system. This system is made of 250,000 shutters that open and close. If you ever observed the night sky in a town or city and compared it to what you can see at night in the countryside, you could probably tell the difference. It happens due to the high volume of light in the city. Therefore, the micro-shutter system will block the irrelevant light, allowing us to see the most faintly lit objects. The light is then dispersed into the spectrum and sent to the detectors. How much light is there in outer space? A huge amount, and in order to capture only the relevant light, the telescope has to be constantly directed at different targets. This will be possible with the help of the Fine Guidance Sensor, FGS. Additionally, scientists from the Canadian Space Agency developed the Near-Infrared Imager and Stiltless Spectrograph, which also
Okay, so there's a lot more to that. Check out the full video. It gives you a breakdown of all the other instruments, and it's a very good explanation. And what we're basically going to do for the rest of the time here is just talk about different components of it in more detail. Now, what I want to do is just explain a little bit more about infrared light and why that is significant to us, and a little bit more about the mirrors, and then we'll do a pause for an intermediate Q&A here if there's any questions that I could answer before we go on past this too far. I also have two other clips here. I'm going to just share the links with those to you, Cheryl, and you can pass them out later if you don't mind. We're going to see more of the images from this part later, so I don't want to spend too much more time on that.
The James Webb Space.
Okay, let's talk about quantum leaps. You've all heard this term, and it's often used a little bit outside of its actual meaning. A quantum leap is often used to describe a very large change or shift or something drastic. And in a sense, it is true. It is a very fundamental step, and very significant, but it's not large. It's actually incredibly tiny. A quantum leap just describes the jump up from, in an atom, the jump from an electron from its ground state, the lowest state that it can be in, up to the next orbital out from the nucleus of the atom. We're going to see over and over that nature wants to reach the lowest possible energy. In fact, you can really describe an incredible range of topics by understanding that nature is always craving the lowest point of stability, and it's always seeking equilibrium with itself. Think of weather, climate in general is described easily that way, just as a high-level description. But the same is true when we look at the quantum world. Quantum world is basically just small steps. The quantum leap that we're talking about is here, at least, is the fundamental position change between the ground state of an electron and then the first excited state. Now, why is that significant, or what exactly does that mean? Well, you've probably seen this in chemistry, and you probably know how to do all the calculations around that, but we're just going to talk about it conceptually here, because this is very critical to understanding the directive of the James Webb and why it's built the way that it is. So there's this fundamental relationship when a photon of light hits any object. We'll just use a generic ground state atom right now, just to keep things real simple, but the concept is true across all materials. The principle is valid. When an incoming photon hits an atom, it brings with it energy. And what does that energy do? Well, when the photon is absorbed by the atom, that energy gives that, if it has enough of it, that is, it will cause that electron to jump up to the next excited state. So it basically that energy is transferred to that leap. It's the energy that it takes to remove it from the ground state and cause it to jump up one orbital outward, just as like you can see on the left-hand side of the screen. Then the reverse happens as well. When if there's nothing to keep that electron in orbit at that second orbital above the ground state, the first excited state is what it's called, it will lose energy and then drop back down. So it's a quantum drop or a quantum leap in the downward direction. And as it drops down, it emits a photon. So basically anything that has matter in it will respond this way. In a very broad sense, this is why materials heat up when they're exposed to light. So if sidewalks warm up when they're exposed to sunlight, the material in that bulk, the cement, is absorbing incoming photons of light, causing a little bit of that energy to be transferred to electrons reaching higher states, and then it cools off at night and emits that in the infrared frequencies that our eyes can't see, but the concept is completely true. So why does this matter? What is Webb doing with this that's unique? Well, let's talk about the photovoltaic effect. If you've ever used those old calculators that have a little solar cell on the window, and then you put light on them, and then you can do any calculations, and then as soon as you cover up that window, it fades. That is the simplest representation of the photovoltaic effect. Basically, when light comes in and interacts with certain metals, it creates a voltage, and that voltage, it displaces some of those electrons and causes a current to flow, and then we can exploit that for a range of purposes. Simplest case is a calculator, but it's also the same principle that causes your cell phone camera to work, for example, or any detector for that matter. CCDs, charge coupled devices, very common these days. They're basically little detectors that have a little current running through them, and then when they have incoming light exposed to them, same thing happens. The incoming photons of light bring with them a little bit of energy. That energy causes those electrons to change orbitals, and then in doing so there's a voltage change, and that can be read as a signal. So it's the principle for not just solar powered calculators, but it's also, if you stack a bunch of those together, you can get a detector that will form an image. Then now all you need to do is make those detectors responsive to different types of light, so red, green, and blue. Now you have a functioning camera representing the visible wavelengths of light that our eyes can see. And if you get enough of them, you get a high-resolution image. So in a nutshell, that's what's happening when you take a picture on your iPhone, for example. It's just taking incoming wavelengths of light, converting that energy into a voltage, and then instead of having just one point of it, like a little calculator window, you're having what are they up to now? 10 million pixels, 15 million pixels? I don't even know. They're huge. It's an immense engineering feat in order to do that. But there's a lot of little pixels there that are doing this exact process with the aid of electronics, and they're made more sensitive with some very clever manufacturing techniques that add a little bit of voltage to them, and they become more sensitive than they would be naturally. But the basic principle is all built on this idea. So let's look at a chart explaining why we use cameras instead of the eye for anything. On the left-hand side, the vertical axis here, this is a logarithmic plot, so just powers of 10, of what's called quantum efficiency. Quantum efficiency just means how many of those state changes in the electron are we able to detect with different sensors or detectors. Now, a logarithmic scale, if you're not used to reading those, just note that each step size increases by a power of 10. So we have 0.1 to 1 on the first step, then 1 to 10 on the next step, and 10 to 100. So each step is 10 times larger. So it's not linear like we're used to seeing. So in other words, changes at the bottom are incredibly small, changes at the top are incredibly large in comparison to the two ends of the scale. And then on the horizontal axis, from left to right, we just have wavelength of radiation. So let's start with what we're familiar with, the eye. Now, what is quantum efficiency? Back to that vertical axis. Quantum efficiency just means how many of those state changes can we detect. So when an object emits a photon, when those electrons drop down and emit photons, how many of those of the available how many of the available photons are detectable? Now, notice the eye is right around 1%. That means that if there are 100 atoms emitting photons, the eye might pick up 1. And that's right in the peak sensitivity range of green, actually. If you look at the right around 580 or so nanometers, that's where the human eye is most sensitive, and it drops off on either side. So we have blue on the right and then red on the left. And you'll notice that they are much less sensitive. The curve goes down, so it means that our eyes are less sensitive to red and blue than we are to green. If you've ever played around with those little laser pointers, you might have already encountered this fact. A red laser that's, let's say, 5 milliwatts versus a green laser that's the same. If they're the same power rating, the green laser is going to appear drastically brighter to our eyes, not because it actually is emitting more power. It's just because that happens to be emitting light that our eyes are most responsive to. So it has our eyes have a higher quantum efficiency of the available light we pick up. We register more of that. The red laser, we just are less sensitive to it. So there might be just as much out there. We just don't pick it up or detect it with the eye. Then a celluloid photograph is still right around the sensitivity of the human eye, actually, in terms of magnitude, but it has a wider range of sensitivity. So you can see that on this chart, it shows that it goes well into the infrared and a little bit into the ultraviolet. But once we start getting into different types of detectors, we can boost this efficiency drastically. So a photomultiplier tube, that's kind of, think of those old school night vision cameras, the green ones that have that graininess to them, if you've ever seen footage from those. They're basically just multiplying incoming photons and then stepping them up through a series of vacuum tubes usually, and then they're just artificially raising the amount of photons that will reach your eye. So it takes one, sets off a chain reaction. By the time for one incoming photon, it boosts it to maybe 1,000, and so your eye is able to make much better sense of that image. But it's still not that sensitive when we compare it to things like a CCD, a charge coupled device. So this is basically what your phone has. Most observatories use some version of a CCD, and Earth observatories as well. So this is the standard technology. There's a range of different types out there that are sensitive to different wavelengths. They can be tuned for different types of work. Some need to be very focused on a narrow band but highly sensitive. Others are more sensitive to a wider band, but they're not as responsive to individual frequencies. Just depends on the mission scope, and that's why scientists spend a lot of time deciding specifically what it is they're going to need to be looking at, pass it off to the engineers early on and say, this is what we need. Now you figure out how to make this work. So the important thing from this graph to understand is that when we use a CCD, we can get upwards of 90% quantum efficiency. So of 100 incoming photons, it'll register around 90% of them, which is very, very good, especially when we're looking at very faint objects that don't emit a lot. So let's look at the mirrors now. The mirrors themselves are a really impressive work of engineering, I think, just all on their own. There's two important pieces to them. Now, we're used to seeing the gold plating, and I'll talk about that in just a minute. But let's focus on the beryllium, the structural component of the mirrors. The mirrors have to be able to function in a very unique environment. Most Earth-based observatories, like the Keck Observatory in Hawaii, even though it's built on the top of an old volcano, very cold, relatively speaking, for Earth temperatures, it's really not that far out of the range of where most engineers are used to building large-scale structures anyway. So it can be built with steel and aluminum and typical materials that are just rigid at normal temperatures that they expect to encounter there. When we say cold, that's a very relative term. Cold to the Webb, we're talking maybe 3 to 5 degrees Kelvin, just above absolute zero. Whereas on Earth, we're cold on Mauna Kea. I think it gets down to maybe negative 30, worst case, Fahrenheit. Not very much. I mean, people can survive in that. So we can use more or less traditional engineering materials for that kind of cold. But when we talk about Webb cold, a few degrees above absolute zero, we have to do things a little differently. Most metals that we would use for typical applications on Earth do not survive or perform well in cold temperatures. And what do I mean by they don't survive? Well, they don't corrode or degrade necessarily, but their mechanical properties change dramatically, and they become very brittle for the most part. They shrink quite a bit. And they are not very useful for carrying large loads for long periods of time because their structural properties aren't the same. For example, a steel beam within the range that you would put in, let's say, a skyscraper. So probably a little over 100 degrees in the summer, probably below freezing in the winter. In that range, it's still going to have some elasticity to it, so it'll give and take a little bit. It can bend without deforming, things like that. But if it gets really, really cold, just a few degrees above absolute zero, it's probably going to become so brittle that any load or transverse load, the shear stress on the side, will cause it to fracture, and then you can't use any of it at all. It doesn't absorb anything anymore. It resists, and then it breaks with much more stress added to it. So there needed to be a very special type of material used on the Webb. And the best material for this type of job is beryllium. Beryllium is a metal that's about 6 times stronger than steel of the same weight, and it's significantly lighter. The problem is that it's incredibly difficult to manufacture. Most of the beryllium that is used today comes from a mine in Utah. There's a little bit of ore that comes up near the surface, and they dig out a couple hundred feet of earth to get to it, and it takes I think over 2 tons to get maybe, I think it's 4 grams that once they refine it. It doesn't come out pure, obviously. They have to do a lot of incremental refinements to get all the impurities out and then polish it down to a material that's usable, and then it has to be heated and cured in a way that it makes it solid and machinable. Now, when it's going to be used in space, it's going to be, again, at the L2 point, so a couple degrees above absolute zero. Now, when we're building it on Earth, we can't replicate those kinds of temperatures throughout the manufacturing process. So every material that has a thermal change will also shrink or grow depending on this. So think of power lines sagging in the summer heat or tightening up in the cold. All materials do this to some extent. Beryllium does that relatively little, but when we're talking about a drop of about 300 or close to 300 degrees total, about 250 Kelvin, it has to be machined a little bit larger. So they do a process called cryofabrication, where they basically machine it under cold temperatures, but they know that the final temperature will be even colder than that. And beryllium is also very toxic to work with, so that's one of the reasons that they like to avoid it when possible. And one of the huge cost factors for the Webb was just getting enough bulk material and then going through these special processes to machine it. But it's machined slightly larger than it will actually be out at L2, and the reason is that when it gets cold, it will shrink the rest of the way. But once it's out there, it will be very stable. It remains very structurally sound even at cold temperatures. Can survive constant movement if they have to make periodic adjustments to the mirrors. Beryllium is one of the best materials for that. It doesn't change shape. It'll conform to the shape that they needed for the optical surface from the beginning. No problem with that. And also because it's much lighter, that is a huge factor in getting this thing launched, because if it was any heavier, then you'd have to start pulling other components because there's a maximum payload capacity on the Ariane 5 that it was launched on. So if the back plane with all the mirror components in it, if that was 6 times heavier, that means you'd have to pull that weight off of other pieces, which might mean there's not much left of the telescope to launch in the first place. So beryllium was really the only option there. Now, the beryllium part that is holding it together is actually not visible from the front, and that's because it is gold plated. The gold plating is it's incredibly thin. It's deposited in a vacuum. It's actually only about enough gold to make 5 wedding rings. Not a huge amount, but it's an incredible amount of surface area that it's going over, but it's just a few atoms thick. Now, why on earth do they use gold for this? This is a perfect example of an engineering trade-off decision. You have to pick not just one variable to maximize for, but you have many different variables that you need to consider and understand how they interplay with each other. So look at the chart here. We have reflectance versus wavelength. Reflectance is just the amount of incoming light that is returned on reflectance. So every mirror that you have, every time you have light passing off or reflecting off of a surface, most of the light will come back, but a little bit is absorbed and converted into heat eventually. So down on the bottom, we have silver, and that's in the violet range or ultraviolet range. You see how it's down around 20%. That means that only 20% of that light is coming back at you, 80% is absorbed, so it's not very reflective. But these different types of materials, you see that as we move into the infrared, they start to get a little bit better. Now, let's see, what is at the very top there? We have silver and copper. They're very reflective, and towards the right, that's where the infrared is. So if we have the blue and the red, silver and copper, looks like, why don't we use those? Aluminum is also pretty good, although I guess the gold is in between there. So let's look at, yeah, copper and silver. So why don't we use those? Well, there's other factors at play. We want something that's very reflective in the infrared range, sure, but it also needs to survive the intended lifespan of the mission, which is at a minimum 5 years. Now, we know now that because of the precision that the ESA launched the scope with, they actually had a lot of extra remaining fuel. Estimates now are that the mission could go on easily 10 years, up to 15 or even 20 if we're lucky. The extra fuel was just to basically serve as a backup or a reserve. So if they needed to do more maneuvering to get to the L2 point, they'd be able to do that and then still have enough on reserve for the 5-year mission. But because they didn't need to do any extra maneuvers, it was launched right on target, right on track, made it without any of the extra fuel being used. Now that can be reallocated to mission use fuel, not launch fuel. So now that that's going to happen, we still have the problem of the 5-year minimum criteria for the mirror. It has to survive the coldness of space and also everything else that space has to offer, micrometeoroid impacts, things like that. How do we pick a material that's going to do that? Well, copper and silver are okay. In fact, they're very good in the reflectance criteria, so they meet that. The problem is that they both oxidize very quickly. So they basically degrade and erode, and then the clarity of the surface drops, and then you don't get useful information. So the light coming in gets scattered in all directions, or you have bare patches where it's just beryllium after a while. So that is not helpful. So that pretty much rules those out. Gold, however, it's a little bit heavier, but it is also comparable reflectance, and it's very inert. So it can survive extended periods without oxidizing with effectively anything. So it's a perfect candidate for coating the mirror in this use case. So that is why they opted to go with the gold. So we have the beryllium mirror to give it strength and shape, and with all those processes used to machine the curve onto the beryllium, then vacuum deposit the gold on it, just a few atoms thick. Now we have a perfectly rigid, precise optical shape with a highly reflective coating that can withstand the harshness of space for the minimum criteria of at least 5 years, possibly, fingers crossed, 20 years. Who knows? Hubble wasn't intended to last 30 years either, but it's still going, so we'll see. Okay, so now we go back to our discussion of quantum leaps and the photovoltaic effect. Let's revisit that and understand why these mirrors have to be that way and why the scope needs to be so incredibly cold. Well, again, on the top right image, that is an illustration of the photovoltaic effect. Incoming light displaces electrons, which causes a voltage. Well, that is helpful when you're looking for a signal, but that concept, this principle, doesn't stop just when you're looking at an object. So you might be seeing a distant galaxy emitting some light, and you're looking for that, but it's incredibly faint. But it turns out that there's a lot of extra noise in the image. And in fact, all objects give off a little bit of radiation. And this is called Planck radiation, and we can look at that a little bit later if you'd like. But Planck radiation, in a nutshell, is the image, like if you've ever seen FLIR footage from, sometimes they show this with police helicopters, you'll see night vision where you can see different, like the engine looks hot, you can see people walking through trees and things like that. They're emitting heat, which is visible. That's Planck radiation. Those wavelengths of infrared light are visible, and they stand out against the colder ground because the colder temperature means they're emitting at a lower frequency, and then that frequency can stand out. So you have contrast between them. So when you have bright objects against cold objects, they can be detected with the light that they emit. And when I say light, I'm talking about electromagnetic energy, spectral energy. When we say light or visible light, that's just specifically referring to generally what the human eye can see. So red, orange, yellow, green, blue, colors of the rainbow. But light extends on, or electromagnetic radiation extends on either side of that. Ultraviolet energy, infrared energy, they're all the same thing. They're just at different wavelengths. It just so happens that our eyes are very sensitive to what we refer to as visible light, but there's really nothing inherently special about that in the spectrum. It's just because that's what we can see that we refer to it. So it's a distinction worth noting, but to instruments, they don't care at all. We just need to know which wavelengths they're looking in. So if we could see infrared energy with our eyes, if we had different types of cells that were responsive to that type of lower, like the infrared energy, then we could see in the infrared. But since we don't, that's where the cutoff happens. But the energy continues on. So why does that matter ultimately? Well, basically, this results in any object that has heat also emits infrared energy, which is infrared light. And that infrared light can cause problems. On the image on the bottom, there's an example of a very familiar case of thermal energy interrupting an image, and that's just artifact or noise. JPEG noise sometimes is what it's called. But on the image on the left, this is taken with a detector that has not yet cooled down to ambient or below. A lot of amateur astronomers will actually put coolers on their detectors so that there is no extra heat being generated by the sensor, because a little bit of infrared heat or that infrared light causes the same process to occur on the top right image. So that, imagine one of, like, let's say the top incoming photon, that's visible light, that's what you want, but you also have a heat source that's giving infrared light, and if you're looking in the infrared, any object with warmth will cause a signal to register, and then it will ultimately crowd the image. So on the bottom, back to the bottom image now, when we're looking at that, we get all this extra thermal noise. That's just heat generated by the detector, by the different components in it, the battery even, or the screen on the back of the display if it has one of those. All of that heat is emitting infrared light, and that's registering on the detector, but we don't want that because it's not part of the signal that we're interested in. So now we have to find ways to shield against that. So when it's cooled down, now you're minimizing the local sources of heat noise coming into the image, and then just leaving open the signal that you're wanting, in this case the beautiful picture of the nebula. So when it comes to the Webb, same principle happens, just on a much larger scale. We just need to keep it as cool as possible because the signatures that we're looking for are incredibly faint and cold. Therefore, any heat generated by the telescope will crowd out the image with unwanted local noise. It's kind of like trying to listen for a whisper in a rock concert. You have to turn off everything else nearby in order to listen up close enough to hear that faint whisper of the signal that we're looking for. So the sun shield, the way that works, they basically are aluminized coatings, and just like the gold is highly reflective to infrared wavelengths, they're using a similar material that's been treated. It's an aluminized mylar film, and it reflects right around 99% of the incoming thermal radiation from the sun. So there's 5 of them. It only takes 4 to get down to the mission requirement. So it rejects enough heat if you just had 4 of them. The 5th one is just for redundancy. So if something happens, if one of them doesn't deploy successfully, which thankfully they did, but now we know that, if that didn't work, you'd have 1 spare. Also, over the life of the mission, there are going to be micrometeoroid impacts. Most of them are going to be very tiny, and they probably won't cause too many problems. But there might be a slightly larger one, or it could hit a critical seam that will cause a tear to propagate through, and then you have thermal energy leaking to the optical side. So the way these sun shields work is, or sunshades work, is by rejecting 99% of the incoming thermal radiation back off into space. And they're actually curved outward so that it doesn't concentrate, or you don't have heat buildup on any one point, because that can cause, if, like, let's say it concentrates near one of the struts that's holding the shade in place, or the shield in place, if it concentrates there, then it might actually cause that beam to transmit a little bit of that heat by conduction to the optical side, which we don't want. So they're bowed outward like a sail, specifically so that it scatters out, kind of like looking, it's convex just like the backside of a spoon. So that way when the light hits it, it doesn't just go back in the same direction. It bounces off in all directions and more or less evenly spreads out the unwanted heat. Then let's go from left to right here. So 99% is rejected, 1% makes it through to the next heat shield or sun shield. Then of that first 1% that made it through, now 99% of that 1% is rejected, leaving now just 1% of that. So it's point one zero 0.01 times 0.01 that's made it through. And you have a power of 10 drop every time. So by the time you reach that fourth one, now you have enough of that thermal energy rejected that it's cold enough to basically block all the unwanted heat noise from the sun. And now you have a cold enough detector that it can start looking for very faint signals of the early universe. And then that fifth one is just there for redundancy's sake. Before we go on, we're going to talk about the L2 point, but I want to just pause and see if there are any questions that you have that I might answer at this point. And if not, we can keep going and save it for the end, but I just want to make sure we get them at the source if possible.
Does anybody in the audience here have a question?
I do. So Aric, on this diagram on the left, wouldn't there be another series of zigzag red arrows on the sunlight side of that mirror? Or am I not understanding it right?
You are 100% right. The way they visualize this, they're making it a meaningless distinction between sunlight and heat. And I think that's a little bit confusing. You're absolutely right. So the sunlight is a broad spectrum. It's not just the visible light, but it also includes with it the thermal energy and then UV and a bunch of other different frequencies and everything else coming off the sun. They're basically saying that all of that is going to be rejected on that first one, and then the heat is what makes it through. The first one, or the first sun shield, is going to have a little bit of a screening effect or filtering effect, so it won't let any of the optical light. I think it's 100% of the optical and even UV light will be rejected at that first one. It's just a little bit of the infrared, the longer wavelengths that are able to penetrate a little bit deeper. So as you go through, there will be, after the first sun shield there will be no more visible light to reject. It'll just be infrared. And then a little bit less of the infrared makes it through each one. So I think that's why they've drawn it that way. But you are 100% right. It would reject not just the heat, but also the full spectrum of sunlight and everything else embedded within that on the first side.
Yeah, Chuck, you have a question?
Did you say my name?
Yeah, go ahead, Chuck.
Hey, why are you worrying in outer space about oxidation without much oxygen around?
That is, there's certain, and I'm not a metallurgist at all, and I wondered that too, and I couldn't really find a great answer. There are some processes, though, when metals are in contact with each other, they can actually create an extremely low voltage and interact with each other. So I don't know the specifics of that. I think that's a great question. I really don't know where that would come from, only to say that the interface between the gold or whatever material and then the surface of the beryllium, over time, that reaction can cause degradation. And I don't quite know the specifics beyond that.
Hi, this is Ed. So the sun screens are, the front one is the largest and then the back ones are smaller. Is that so that you can tilt the sunscreen by 20 or 30 degrees with relation to the sun without any of the back screens being illuminated?
They're actually really close in size. My understanding is that the step down is more to do with the packing configuration than the thermal properties. The first shade is largest because that's meant to have full coverage and then cast the widest shadow over the remaining equipment. So that way it's just a little bit of a margin of error, I think. But I don't think that the step down is for any other reason than that.
That implies that you can actually move the telescope in relation to the sunscreen, and you don't have to tilt the whole package to select targets.
Right. That's a good question. We'll actually get into that just a little bit. Excuse me. Momentarily. The scope itself will not be able to move much. It does have a little bit of range of motion, but it doesn't pivot and steer in the same way that most space telescopes can. It's more or less locked to looking directly away from the sun. And within that band, it can see a little bit. It can pivot up and down ever so slightly, and it can track. But you can't. There are actually huge amounts. This was a big part of the early discussion. The scientists, of course, wanted to be able to look at any point in the sky, but the realities of this orbit mean that it's only able to look directly away from the sun within a very narrow cone. So we basically have to look at objects that are in that range within, and then you can fine tune it, but it can't move much at all. So the optical telescope element can't maneuver itself around the sunshade. The sunshade is always going to be aiming directly at the sun, and then it will be, the optics are on the permanent shadow of that, and the shadow that it's cast on is wide enough that no matter where it pivots within its limited range of motion, it'll always be covered by that. And we'll actually, the very next thing I wanted to talk about was the L2 orbit and explain a little bit more about that. So maybe that'll add a little bit more.
Yeah, I'm excited to learn about that L2 orbit. Anybody on Zoom, would you like to ask a quick question?
Patrick has his.
Patrick, go ahead. Patrick, we can't hear you.
How about now? Yes, that's good. Okay. Slightly nerdy question. Do you know anything about the difference between CCD and CMOS cameras in this application?
That is an extremely nerdy question, and I love it. There are different properties. They respond differently in the infrared and the visible wavelengths. My understanding is that the CCDs are significantly more responsive to infrared wavelengths, whereas the materials that you would use, the limiting factor for any detector, you have to, or not limiting factor, but the very first consideration you have to make is what material you're going to be making it out of. So if you want to be looking at infrared, for example, you need to find metals that are responsive to the wavelengths of infrared light and that generate a voltage in return. My understanding is that the CMOS sensors have a much more shallower penetration into the infrared, whereas CCD detectors, they're first of all easier to cool, and they're, I guess, more reliable nowadays just because the engineering expertise has increased, but also the materials, the metals that are used that are responsive to those different wavelengths are just easier to manufacture as a CCD than the more limited CMOS. So there are CMOS detectors out there, but my understanding is that most observatories have migrated towards CCDs, and also the consumer world has heavily moved to CCDs. For different but somewhat overlapping reasons. They're just easier to produce on large scale and more reliable, and lower noise rates from my understanding. But I could look more into that because I'm a little more curious now that you ask. I don't know a whole lot more than that.
Okay,
That's great.
Thank you, Patrick. But no more nerdy questions from the audience. Does anybody in the audience here have just a regular question? Okay, go ahead, Aric.
I have a question on Zoom, if I.
Okay, go ahead, John.
We know when the Hubble launched, there was a problem that was discovered only once it was fully launched in orbit, and fortunately, we were able to do something about it. Do you know of any contingency plans should there be something discovered only once? They're gathering images and trying to fine tune. Is there? We know it's not as accessible. Is there any kind of contingency plan or anything we can do there?
No, it's pretty much one and done. But that is not necessarily bad news, because the factors that caused the Hubble malfunction That's the nicest word I can say about that. That was basically human factors. That was not anything to do with the engineering itself. It was the bureaucracy and the red tape, and it was contractors not going through the full testing process. And it's been a while since I've looked into that, so I'm a little fuzzy on some of the details. But my general understanding of that is that the contractors got competing sets of information, and they didn't want to go through the more laborious testing process to validate on the ground, because the mirrors are very difficult to move, and it was a cost-cutting measure, I think, to not move the critical assemblies around as much as needed. So they did a test to verify that it was manufactured to spec, which it was, but the specs themselves were not in agreement, and that's something you would have detected if you had tested it in situ on Earth. But the Webb has been the most scrutinized scope yet. That's part of the delay. I know there's a huge, a lot of people were frustrated when they kept pushing it back. It's over a decade behind schedule. It's a little frustrating when a lot of the coverage over the last couple of years has been about how far behind and how costly it is. You notice how almost every article mentions the $10 billion James Webb. Like, yeah, we get it. It is expensive. Why don't we do that when we talk about the F-35 or something? It gets a little bit of negative connotations, I think. But the reason that price tag is so steep is because they are vetting everything possible on the ground. Not only did they pause the production to go through that second design review and analyze those 400 single point failures, that's to make sure that nothing could go wrong that they miss on the ground, but they also checked every single system as it was in use. So there's some things that are just not possible to test until you're actually out in space. But everything that they could do, they did do. There were no corners that were cut this time. And it's not that it was a corner that was cut. It was more of a just philosophy of efficiency versus cost originally. Like, can we get close enough to verify and feel comfortable, but not actually do it? With the Webb, they just basically said, let cost not be the limiting factor here. Let's check everything. And I think they were more inclined, I don't know how you'd prove this, but I suspect at least that they were a little more open to getting the engineers' feedback this time and letting the administrators say, like, what do you guys need? Can we do it? There's always going to be, there's a perpetual tug of war between administration and engineering. The engineers, if they had unlimited budgets, it would be a $100 billion telescope, and it would almost certainly work without a hitch. But now, can we cut that down? Are there ways to balance that? And I think they erred more on the side of caution this time. So I don't think there's going to be any issues. We've passed like the launch and the sunshield deployment. Those are the two most critical. No issues there. So it's very unlikely that something's going to go wrong from here on out. But if it does, we're not able to service it. It does actually have a mating ring on the side. And that was kind of an earlier design item that was left in. It doesn't really, there's no serviceable parts on it. So even if we did build a robotic scope out there or service mission, there's nothing that can be serviced externally. It would have, every part has to be done by the contractor that built it. You'd have to take it apart, and it'd have to be an Earth-based thing. So that's why so much effort went into testing and validating. But no, once it's out there, it's on its own. But it's very likely to succeed.
Thank you.
Okay. Thanks, Aric. I think we have one more quick question, and then we'll give it back to you, Aric, okay?
Sure.
So maybe I missed this because I came a little late. Is this a multi-country, the best people from any country working on this project or worked on this project? Or is this a US-based project? And if it is a US-based project, are there top secrets that are not allowed to be revealed? Because who knows?
Yeah, great question. It is a multinational project. So the ESA and NASA were both involved. They were both the prime agencies, I guess you could say. But it incorporated a lot of universities from around the world. NASA was the prime agency, I guess, and they delegated responsibilities to contractors and universities and academics from everywhere. There are no top secret or even secret components on this. The closest it gets to anything like that is that just in aerospace in general, because of the nature of the field, a lot of materials that you use to design a space telescope or anything that's on a rocket can also be used for military purposes. So for that reason, there are some they're not secret, but there are some materials and processes that are designated as U.S. nationals only. So when I was working on the Orion program, for example, there's nothing classified on that at all. But when it comes to the certain materials and importing them, they have to follow a chain of custody. And there's certain materials that when you're talking to somebody who's a partner on the ESA side, you can't give them certain information, not because it's secret, it's just because it's dual purpose, aerospace and military. But the mission itself and most of the materials, everything that is done, thankfully is completely open. The limiting factor really to getting information on the James Webb is just your own patience. I've been able to find an incredible amount of information on it, and it's all openly available. You can find all this online, so you can speculate, but there's almost no distinction when it comes to the basics of building a missile, though. Apart from like the payload and the warhead or whatever you want to put on it, the way that objects move through the atmosphere or into orbit is identical for spacecraft and for rockets. And so that's where the only potential conflict of interest shows up. But the nations that are involved are very trusted allies. There was some, it's been a while since I came across that, but I remember reading something about, I want to say it was either, I don't want to get it wrong and misname that, but there were some countries that were not included in the project just because of the risk of information spill outside of the approved uses for this. So you can find just about anything you want on this online, but as far as the actual mission scope, there's nothing classified about it. Everything is open and democratic, and in fact, the calls for research on this, so the people that compete to get time on the telescope, those are not even all set in place. They set the first round, but it's open to anyone in the world who has an interest. You just submit a proposal. NASA makes available all the specifications for the instruments, so you can see exactly what they're capable of doing, what kinds of data you're able to capture, in what resolution, and then you and your team build up a case for what you're studying, why it's important to the body of knowledge, and how this will advance science. And then you spell out in great detail how those instruments will serve that purpose and why you should have time on that. And basically that's why so many people were excited when the mission had reserved fuel now, because we could easily double the lifespan. That means we'll get double the amount of research time on it. So the competition for the first 5 years is incredibly steep, but now that more years potentially open up, that's good news for everyone involved. But as far as classified information, there's nothing like that. Everything about this project, thankfully, is open. The ESA and NASA were the two big agencies involved, but they delegate, subcontract different parts out, and then universities from around the world were in charge of overseeing the development of the detectors on there, separately from that will be involved in the research that it's going to do. So it's a very open, multinational project. I think can serve as a great model for the future. It's not without its hiccups. There's always there's red tape from NASA. Then you have red tape on the red tape when it goes to ESA and back and forth, and it does delay things. But the fact that we have multinational input and buy-in means that it's more of a worldwide project, and I think that's best for everyone. At least in a philosophical sense, this is benefiting humanity, not one nation. And I'm very excited that the information and the research from this will be open to the world as soon as it can be. As soon as the teams are done with their studies, there's no barriers to that. There's no paywalls or embargoes of the data. They make it publicly available, just like Hubble. And it benefits every single person on the planet for knowing that. We live at a time unlike any other, and I think that is incredibly important that we don't hoard our expertise and knowledge. I think everyone deserves to see what it's going to uncover, and I'm glad that they're continuing on with the web this way. All right, we'll do another Q&A session here at the end. well, let's see, we have about half an hour, so I want to cover the big points here. Let's start with the L2, the Lagrange point. I know that's kind of an interesting concept, and it can be a little bit confusing. And if there's one point that I have seen more unintentional misinformation on, it's probably this point here. Lagrange points, they can get messy, so we're not going to go into the math at all. I think it actually just is a very simple conceptual explanation will suffice. Let's start with the Earth and the Moon briefly. Now, imagine that you're standing on the surface of the Earth looking up at the Moon, and you launch in a spacecraft up towards the surface of the Moon. Well, we know the endpoints. When you're standing on the Earth is pulling you down. When you're standing on the Moon, we've all seen the pictures of the astronauts. We know that they're standing on the Moon. So at what point in there was there a flip? Conceptually, would it make sense that there's a point that if you perfectly stopped there, you would fall towards neither the Earth nor the Moon? You'd just be perfectly still. And if you move to one side of it, you'd slowly start falling towards the Earth, or if you move to the other side, you'd slowly start falling towards the surface of the Moon. Well, conceptually, that point is called a Lagrange point. That would be the Earth-Moon Lagrange point 1. And that is basically what's going on. If you are on that point, you are perfectly balanced between the gravitational pull of the Earth and the Moon. So if you're on the Moon side, you fall towards the Moon. If you're on the Earth side, you fall towards the Earth. If you're right on it, you just stay there. Now, we are talking about, with the Webb, we're talking about an Earth-Sun Lagrange point, and it's the second Lagrange point. There are 5 total. They're a little bit harder to visualize, but in fact, let me move for a second. Let's go to the Earth-Moon point. The L1 point that I just described, that's this thing right here. So the field lines here are showing gravitational potential. And if you're used to reading like a chart, a topological chart, for example, the denser the lines are, the closer the lines are together, that just means that there is a steeper slope. The further spread apart they are is a gentler slope. So the Earth-Moon Lagrange point 1, that's the point where I was talking about. If you parked an Apollo spacecraft right there, you would fall towards neither one. You'd be perfectly balanced in between them. Anything on the left, you go to the Earth. Anything to the right, you go to the Moon. Now, there's another point on the back side here. This is called the L2 point. This one, I think, is one of the easier ones to conceptualize if you understand how things move. Let me try and draw on the screen briefly. Maybe I can't do that. Well, okay, I'll just describe it. So as these objects are moving around, imagine them moving counterclockwise. So the Earth is fixed in the center of the frame. The Moon is moving counterclockwise, just by arbitrary convention here. Now, an object's orbit is determined by its speed, not its mass. This is why an astronaut can do a spacewalk outside of the space station. While the space station is many tons and the astronaut is only a few hundred pounds, they can move at the exact same speed because, despite their different mass, because they're sharing the same orbit. It's the speed that determines it because they're moving together. Now, an object that's moving further out from the Moon, further off on the right, past the L2 point, it would by necessity have to go significantly faster. The natural speed that it was going around, if it's outside the orbit of the Earth, the Moon would start to overtake it. Sorry, I said that wrong. If it was moving outside the orbit of the Moon's inner orbit would eventually overtake it. It would move a little bit slower as we go out. And we see that with the orbits of the planets. The further out you go, the slower they tend to move because they have larger orbits to go over. Now, as you get close to the Moon, you start to feel not only the gravitational attraction of the Moon, but also the gravitational attraction of the Earth. So it's the Earth plus the Moon that are pulling on each other on an object now that you place at L2. So think of it as like holding hands. It's a gravitational handshake, and the combined pull together of the Earth plus the Moon is significant enough that as it moves around, it can actually maintain a slightly tighter orbit at a slower speed. So if the Moon wasn't there, the object would go faster and faster, slower and slower, and the Moon would eventually overtake it. But by being held in balance with the Earth and the Moon pulling together on that object, it can orbit counterclockwise at that distance L2 from the Earth, and it will move slightly faster than it would normally. So gravity's pulling it along, and it will always be permanently locked right behind the Moon, in the Moon's shadow. So let's go back to this image here, now showing the Earth-Sun Lagrange point. It's the exact same concept. Now just replace the Sun with, or the Earth with the Sun, and the Moon with the Earth, and then we get to the exact same thing. The principle holds true in exactly the same way. At L2, the gravity of the Sun plus the Earth means that it's able to maintain an orbit directly behind the Earth at all times. So Earth's gravity pulls it around with it in its orbit around the Sun. So the advantage to this is that it's never further than L2 away from the Earth. Now, we want it far away from the Earth so that it's not picking up that extra thermal radiation from the Earth. The Sun's radiation is going to be more or less the same anywhere. So we need it to be far enough away that we're not picking up extra unwanted noise and heat from Earth. But also, it doesn't, the Webb itself does not have unlimited power. Even with its solar panels, it can't transmit across, let's say, the diameter of Earth's orbit. So if it was truly orbiting the Sun on its own orbit, separate, uncoupled from the Earth, it wouldn't be able to be in reach. It would need a much larger power source in order for us to get the information back. So by being close to the Earth, it's 1.5 million kilometers away from the Earth, but we build an antenna that can, and design the solar panels, size them appropriately, so that it has enough power to just send information that distance, but no further. But because it's locked in the Earth, or with the Earth now at the L2 point, Earth and the Sun pull it along, so it's always right behind Earth, directly opposite the Sun in the sky. And because of that, it doesn't need to have fluctuating strength in the antennas. It never needs to go further than that distance. So it's able to sit at that point and use very little fuel. Now the fuel that it does use is to go around this little arc. And you see this little circle thing happening here around the L2 point? That's because it's actually not precisely at the L2 point. If it was truly at L2, it would be locked in the shadow of the Earth. And if it was in the shadow, it would not be able to receive any sunlight and therefore no solar power at all. And it doesn't have any onboard power. It has some batteries, but it doesn't have a continuous power source. So the fuel that it has is actually used to maintain what's called a halo orbit, where it just slides around that gravitational potential, around the L2 point, just a little bit. So it's constantly falling downhill, kind of like a coin in one of those, I haven't seen them in a long time, but those little coins that run around in the mall that constantly spiral inward. It's kind of like that, except it never actually goes downhill. It's always moving around that point, but never actually gets there. So the fuel is just to maintain that orbit as needed and make very micro adjustments to that. But the halo orbit takes it just outside of the diameter of Earth's shadow, so it's always peeking around the limb of the Earth and therefore getting direct sunlight and able to receive solar panel or solar power. And then the sun shields block the unwanted heat from the sun. So you have to have sunlight for power, but you have to block it with the sun shields. So that's why it's designed that way. It can only operate at this one particular point. So what does the moon have to do with it? Absolutely nothing. It's completely independent of the Earth's or the Earth-Moon system. It's always going to be the same distance from the Earth. It's always going to be directly opposite the sun. It's the combined gravity of the sun and the Earth pulling together on that point that keep it in gravitational tugboat around the orbit of with the Earth every year. So it's always going to be relative to the Earth and the sun in the same point. The moon happens, you can see to scale actually how small the moon's orbit is. It has nothing to do with it. In fact, it just causes minor perturbations to the orbit, and that's one of those small adjustments that need to be continuously made with the fuel on board. But that's relatively minor compared to the fuel it takes to get out to that point. And when another interesting little tidbit, when it was flying out to the L2 point, it's flying uphill gravitationally speaking. So it's much the same way like when you throw a ball straight up in the air, all of the energy is at the front of the launch, and it eventually slows down, reaches that top point, and then stops for a brief moment. That is what we're doing with the Webb. The reason all the burns happened at the very beginning, it has all of the energy at the front, And the burns are just designed to get it right on that trajectory, and then it continuously slows down and slows down and slows down. So it covered something like 80% of the distance in the first, I think, week or so. It was a lot, and then the rest of it is just slowing down. So it takes a long time, and then it completely runs out of energy when it reaches that L2 point, and then it parks there indefinitely. The reason it was so critical to add multiple burns that are all just a little bit on the conservative side. They aim just a little bit under and build their margins on the low side, because it doesn't have thrusters on the optical side, which is facing away from Earth. So if they overshoot it at all, they have no way. They don't have a reverse gear, so to speak. There's no way to fire reverse thrusters. It can only go towards that point, never away or back up from. So that's why it was so incredibly paramount that they get it precisely right, and they don't overshoot even a little, because they can't pull it back. But they can underburn if they need to, and then just add very small amounts forward, but it cannot go back from that point. Okay, so that's the Lagrange point. Now you see why it's not that hard to understand conceptually. It's just hard to fit that into a headline. So I've heard a lot of points saying that it's orbiting the sun and not the Earth. Not entirely true. It is past the moon, but it's not related to the moon's orbit. There's just a lot of little, I guess, looseness in the way it's described that makes it a little bit harder to understand, because they don't all agree. So now you know what's actually going on, and one of my goals here today is so that when you see headlines in the future, you know how to read between them a little bit and understand a little bit more about what's actually going on, and take little bits of information and add on to what you know about it now, so you get hopefully more depth to the coverage. Okay, this is just interesting. This is an image. This is on the left-hand side. This is from that L1 point, from the Earth-Sun L1 point, Lagrange 1 point, taken back towards the Earth with the moon crossing in front of it. So that's not a composite. That's actually a spacecraft looking at the Earth, taking a picture of the Earth, with the sun directly behind it, and in the same frame, the moon is crossing in front of it. And you can see how much darker the surface of the moon is. In comparison, it's a comparison we never get to see, obviously, from the surface of the Earth, because we can only see the moon outward. We don't see them side by side. But the Earth is much more specularly reflective. The atmosphere, the white clouds, a lot of water vapor are very reflective, and then the oceans, of course, the water reflect back a huge amount of sunlight. And then you can see that the surface of the Earth, like the continental masses here, like Australia down there, compare that to the surface brightness of the moon. They're roughly the same, even though there's a distance factor in there. But the surface of the Earth is made bright by the atmosphere and the water, and because so much of the surface is covered with that, it makes it a very, very bright planet in comparison. Let's see, size comparison. Let's not go through that. I think that's we've covered that mostly. Let's talk about infrared light. So we've talked about how it's going to look in the infrared. Now let's talk about why that matters. So infrared light was discovered by William Herschel. This is just a fascinating story, one of the most important breakthroughs, I think, in early optical science. And basically he discovered that Newton had made the concept of splitting light into its constituent colors. That was pretty well known. But he wondered what would happen if there were different properties to those different colors. And so he basically put thermometers, a mercury thermometer, on the different wavelengths of light as separated out by a prism. And the discovery was that at the low end, each color did have a different temperature, and he noticed that was consistent. So that by and itself is already quite significant, to notice that the different, like red and green and blue, they even if they're all being split from the same source of white light, they don't necessarily correspond to the rise in temperature. They respond differently. What is white light? Let me just do a quick aside. White light is not an actual color of light. White is a neurological way of interpreting the presence of all colors. And in fact, I think it's mostly blue and yellow. If those two are there, our eyes basically read that as a shade of white or off-white. But when all three colors, red, green, and blue primary colors are there, even though our eyes are receiving signals through the three different types of cells that respond to that, there's a chemical reaction. Once it registers the presence of all three red, green, and blue wavelengths of light, or some spread of those at least, then it processes that as white. So when you're looking at your screen right now, The white points, like the white text, if you look up close, you'll see red, green, and blue pixels on there. You can separate them out as much as you want, but when they're taken as a whole, when your eye processes them as a collective spread as opposed to individual components, it turns it into what we perceive as white. But white is not a color, and that's why you'll never see white defined as a specific frequency of light or a wavelength of light. It doesn't have one color. In fact, it's that the presence of the entire continuous spectrum of visible wavelengths all present simultaneously. So that's why you can break white light into colors. Now, the interesting discovery, though, that Herschel made was that, and I believe, and this might be more apocryphal, who knows, but that he discovered that after he left the prism open to the window, and he was done taking measurements, the sun moved a little bit, and then he noticed that the one that was seemingly out of the light, so a little bit below the red color, he thought that it should be reading room temperature at that point, but it was actually picking up some heat. It was actually getting warmer than the others. So he repeated this a couple times and found he controlled for the different factors and found that indeed there was an invisible wavelength of light somehow coming through and causing a rise in temperature. And what he discovered is what we now know as infrared light. And in fact, light is not just what we see, it's part of a continuously variable spectrum that we can do all sorts of things with. Visible light is just a very narrow band that like I said earlier, our eyes are responsive to, but there's nothing inherently special about that. Infra just means beneath, and then ultra means above, so that's where we get ultraviolet and infrared. The infrared light is where the Webb is primarily going to spend most of its time, but if we look further past that, longer wavelengths, we have microwaves, which we're all familiar with because we can use them to resonate with water molecules. And that's where our microwaves in our kitchens take their name from. But then we also have radio waves, which they have important properties because they can propagate long distances over land and through the atmosphere, and they can bounce. And then X-rays and gamma rays, ultraviolet rays, they all have their different applications on Earth, but also in astrophysics as well. Now, what does infrared do for us? Well, let's look at where we're covering with the Webb. The Webb is going to be focused on the near and mid infrared, whereas Hubble did a little bit, it had the full visible spectrum plus a little bit of ultraviolet and then the near infrared. But here, the Webb telescope, you can see, is going to cover just a little bit of overlap, but there's no visible light, and it goes from the near to the mid infrared and then overlaps a little bit with the Spitzer. Now, what can we see in the infrared? Why is that important? Well, there's two major factors. The first one is cosmological redshift, causing all of the visible light from the early universe to have shifted as the universe continues to expand. The space in between us and the distant early universe is now shifted towards the red end of the spectrum. So all of that visible light is now moved towards the red end, and there's nothing visible to actually see. Sometimes this is referred to as Olber's paradox, when it's a classical question about why the sky isn't entirely filled with light. Because if you keep zooming in with larger telescopes, it seems like there should be more stars the further out you go. And the answer is that, simply put, they're there, but the further back we go, the further away, and therefore the more expansion between us and it has happened, causing the light to shift to the red side, where our eyes are no longer able to pick it up. Now, this was one of the early goals of the Webb. That was not novel or new in any way. This was an area that scientists already knew they wanted to look at, and that was why they built the Webb in this area. The reason it's so large is actually less to do with the region that it's looking in and more to do with resolution. Aperture it gives you two things. It gives you light gathering ability, so that cuts down on exposure times, and the other thing that it gives you is higher resolution. So for example, the Hubble Deep Field, if we were to image that same area with the Webb, now the big difference is that we'll be looking in the infrared as opposed to any of the visible, but those small features will will have more detail. The size, in other words, the size of the smallest feature you can see is tinier, meaning there's more information. So just like a larger resolution camera, if you have more megapixels on that and image the same area, you can see more detail. Roughly, that's what's happening when you increase the aperture of the primary mirror by this much to 21 feet in diameter. Huge light collecting area. We'll be able to see several times more detail, so smaller features than we could ever with the Hubble for that reason alone. So the aperture is what gives us resolution, the gold, and then the detector range gives us the infrared. Now, let's look at the Planck radiation one more time. We've talked about that a little bit, but this really drives home why it's important to understand how cold it needs to be.
Aric, can I interrupt real quick?
Yes.
We've got about 10 minutes left for our meeting. I
Okay.
do want to allow for a few questions towards the end. I'll kind of leave it up to you if there's like one main thing, last thing to present. But yeah, this is so great. I hate to interrupt anything, but
Sure.
we do
No.
have 10 minutes.
Totally. Absolutely. We'll just end on this point. This is the last significant thing that I want to hit on today, and then we'll open it up for questions. So just in this Planck radiation chart, this is just showing the wavelength of light and the corresponding energy associated with it. You can see the visible wavelengths here, and then as we go to the red end, things start to get very cold, 3000 Kelvin all the way down. So it doesn't actually show it here, but the signatures from the early universe when it's incredibly cold are very, 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 very low. And that's why we need such high sensitivity. And let's put that in a different perspective. This is a direct comparison of how Hubble and Webb, how far back they're able to look. The further we go back in time and in space, they more or less become the same thing at a certain point. Or related, not the same thing. But the near infrared shows us only up to a certain point, and that's where Hubble was able to get. But if we go further back, we have the cosmological redshift, which causes frequencies to be shifted towards the red end, but they also become fainter and colder. So the colder an object gets, the lower, or it emits light at a lower frequency, and then we have to have a very large sensitive detector, which is where the Webb comes in. And that's why the Webb needs to be very, very cold. In fact, it has to be that cold because that's the temperature of the early universe at the very first stages of formation. If the ambient temperature of the Webb is warmer than the objects that it's trying to image, it will drown it out with its own heat signature. In other words, it'll create its own noise, and we won't be able to see that. So that's why it needs to be so cold, because we're looking very, very far back to the cold early universe, just after the Dark Ages, about 370,000 years after the Big Bang. The Webb will now let us see the formation of the earliest sources of light, or just on this side of it. There might be further back that we can go, but the Webb will represent the furthest back step in time we've ever been able to take. This is just the last image I'll show, explaining the concept of the light shift, or the redshift, as we go further back in time. The other advantage that the Webb will offer in the infrared, and this was not a primary design goal, this is just something that came online years after it was already in development, is the discovery of exoplanets. And exoplanets can be studied in the infrared, and when we detect their shadows as they transit in front of their host stars and the shadows cast towards the Earth, we can detect certain spectral absorption lines, like the presence of water, for example, is a big one. But we can study atmospheric composition of exoplanets in a way that we haven't been able to yet, enabled by not only its infrared wavelengths or sensitivities, but also the large aperture. So as a planet crosses in front and if it has a hypothetical water in the atmosphere, the water will absorb certain lines of the host star's light spectrum, and we'll see that with the Webb in a way that we just are not able to quite study as in detail. So let's open it up for questions. I'll just leave this image on the screen here showing the Carina Nebula imaged in visible versus infrared light, and the Webb's capability of seeing in infrared, and how the light is able to go through dust and gas in between us and the source and let us peer through clouds effectively. So this will make studying the Milky Way, we'll see it in a new way that we have not yet so far, because we just haven't had that much resolution, but we'll also see early galaxies in their earliest possible state just after the formation of the earliest galaxies, and even stars. And then we'll see new exoplanets. So exoplanets, our own galaxy, and the earliest possible light in the universe is what the James Webb will leave us with. So with that, let's open the floor for quick Q&A. And if we don't get to them all, my apologies. You can always send me an email. Cheryl can put that information out there, and I'd be happy to talk to you more. I don't want to hold you past the end of your meeting here, but I'm happy to stick around as long as anyone would like to be here.
So
Okay.
Aric, I have a question. My name is
Hold
Jeff.
on one second. Mike had his hand raised earlier.
sorry.
Let me have Mike and then we'll get you, Jeff.
Okay.
Mike, go ahead. You have a question?
Yeah, just a couple, and I think you've already answered them, but people have asked why not have an optical scope, and I'm guessing because it can't really give us any additional information. Is that correct?
In short, yes. The areas that we would see optically have been studied at length, both from ground-based observatories and with the Hubble. So there's always more that we could image, and the Webb can't see more than that band directly behind the sun even. So there are so many things that we won't be able to see. But when it comes down to it, the science objective was to study this region of the spectrum as opposed to a particular point in the sky. So I guess you could think of it as building a telephoto lens to look deep in the forest. We're going to be seeing the distance for the first time, but the next step in the future might be to get a comprehensive view of the entire forest. Here, we're only going to be able to look in the areas that the Webb can see. Optically, it doesn't offer much new for us. Now, would it be incredible to have an optical telescope with this aperture? Absolutely. And to that extent, I hope they keep funding larger and larger telescopes. But the next critical area that hasn't been studied is in the infrared. So that's why they're focusing on that. Hopefully, we'll see a large optical telescope at some point, because that would just be absolutely phenomenal.
Okay, well, we're still going to see cool images like this because of false color, I guess. But just one other sort of interesting trivia point from the biologist here. When you were saying we perceive white light, just basically because that's what our eyes do to make us see something. I thought it was interesting when I read this a few years back. Babies actually see more of the blue spectrum. So when they first come to look at the world, they're actually seeing stuff with a fairly clear blue shade that we could only see with special glasses.
Oh, interesting. I didn't realize that.
Yeah, it's a biological point. Oh, my only other point. I'm really upset that I didn't get here much earlier so I could hear all the other stuff, but I'll look at the recording.
Oh, sure. Yeah, well, we just covered the basics. There's so much more out there. It's an endlessly fascinating topic.
Okay, Jeff?
So Aric, I have a question about the L2 point.
Mhm.
Since it's in the backside, the Earth is between the sun and the L2 point. Does the L2 point offer more shading of the radiation from the sun onto the Webb?
Yes. If it was precisely at the L2 point, yes, it would. Because it is in that halo orbit that takes it just outside of the L2 point, it's always going to be, if this is the Earth, the L2 point would be here and it would be perfectly in the shadow, but it's going to be just outside that, so it's always going to get full sunlight exposure. So the key advantage from a noise perspective is that it's far from the Earth, so it's avoiding all of the terrestrial radiation sources that we have. Earth emits a lot of heat by itself, and then there's also artificial sources of thermal energy or just spectral interference that we don't need. So being far away from the Earth, it takes that out of the equation mostly, but it's getting full exposure to the sun for the sake of power.
Thanks. Is it also true that you're getting a higher communication bandwidth because you don't have to fight the radio noise from the sun?
I'm not sure that that's related. That's a good question. I don't think that that's part of it. I think that it mostly has to do with or whatever problems there are as far as factoring out solar influence. That's been well studied, and deep space missions have had to contend with that since the early days of even Voyager. So the Deep Space Network, which will be used for the Webb, it's already used to receiving and filtering out unwanted signals from there. So however they're handling that, I don't know specifics, but I know that it's not novel in this case. They're just relying on the existing infrastructure for that.
Any other questions?
I've got a statement. This is not so much a question as a request, Eric, but could you let us know how we can contribute to Stanley Lake Stargazing? Because I was going to donate after your last talk, but I couldn't really find a good way to do it anywhere. You can become a Patreon member, I guess, but I just wanted to do a one-time donation type thing. I couldn't find it. But if you could send an email to Cheryl or whatever, maybe she can forward it to the group.
Absolutely. That's a good question. We just became a 501c3. Actually, we just received approval this last week from the IRS. So we're changing how we handle that. But from here on out, any donations made will be tax deductible, and we can get you a receipt and all that. So I don't exactly have information right now, but I will follow up with Cheryl about that. And feel free to forward to all your rich friends.
Yeah.
And we're also, I also encourage everybody to donate to Stanley Lake Stargazing, because we're helping for them to purchase telescopes that we will then share when we schedule another stargazing event. And so the money that we donate, we actually get to enjoy those telescopes as well.
So are you going to advertise those meetings on Boulder Atheist as well as?
Yeah, our last one was in September, I think. We had kind of a fall stargazing.
With the rain.
We may want to do an April one. We don't want to do summer solstice, because then it takes forever for it to get dark. So we kind of the equinox times, I think, are the best, right, Aric?
Yeah, that's true. And actually, I can send you. We're finishing up our summer schedule here. We're hoping to have that out in the next couple of weeks. But we'll have regular star parties for the public. Obviously, when we do one with you guys, it'll just be for your group. But we do have public star parties every week in the summer. This summer we'll have some with Stanley Lake Public Library, the Broomfield Nature Programs, the Broomfield Library as well. And then we'll have some at a couple of parks here in Arvada, and then at Majestic View Nature Center. So there's plenty of ways to come out. This year we actually have a few new scopes as part of the fundraising campaign from last year. But we also are setting up an imaging station. We're doing indoor stargazing as well on colder nights. So you can take pictures of the moon through the computer. You can control the telescope, steer it around. You can also take pictures through your smartphone. All sorts of fun stuff. So come out to one of those star parties, but we'll definitely schedule something just for the Boulder Atheists at some point, maybe April. That sounds good.
Perfect. Thank you so much, Aric. We really enjoyed your presentation.
Yeah, my pleasure. Happy to be here as always.
Thank you, everybody.
Thank you.
Thanks, Eric. That was great.
Oh, absolutely.